Alright everybody, today we are going to continue with our investigation into hypothesis and significance testing, and we're going to continue that with the chi-square test for independence. But today's goal is not just to introduce that test for independence, but now it's start to formally define all of the components and key steps to doing a significance test. And we'll do that in the context of the chi-square test for independence. So that's really ultimately what our EQ is. When we get to the end, what do? How do I interpret the results of a hypothesis test? Well, let's take a look at some reading from this first page and have you guys jot down a few notes. A very common job in statistics is to evaluate some sort of claim. What kind of claims are these? Let's look at a few examples. A tech company might state that only 0.5% of all their devices have a lifetime less than the warranty period. You might start to think to yourself, well, hold on. I've owned a lot of phones that have died completely or crashed well before that 2-year warranty period ended. And that doesn't seem quite right. I'm going to call BS on that. Now, there's another example here. An administrator at a school states that students that score high on the English portion of the ACT don't score well on the math portion of the ACT. And you might think, wait, I know people that are good at both. I want to investigate that claim. I don't know if that's really true. Here's one that's maybe a little bit nearer and dear to all of our hearts. Yelp reviewers of a popular restaurant chain state the foot-long sub sandwiches, on average, are not actually 12 inches long. Are you getting shortchanged on your sub sandwich? Do you need to open up a class action lawsuit to the benefit of all humanity to make sure that you are getting your foot-long sub as advertised? We could do a statistical test by collecting some good, solid, unbiased data and assess this claim. Another one, a candy maker states the distribution of colors of their most popular candy follow a uniform distribution where all 5 colors are equally likely to come in a pack. Have you ever gotten a pack of Starburst and every single one of them is orange? Or very close to it? Hey, maybe that distribution is really not all that uniform. Maybe they're just trying to unload a whole bunch of orange candies on you. Who knows, right? But these are the things that we can start to take a look at with significance tests or hypothesis tests. Often somebody's going to make a claim that you are skeptical about. You want to investigate it. So to investigate, you're going to make some unbiased observations by collecting some data, and then you're going to compare your observations against what we would expect to see, assuming that the claim made is true. And this is kind of our key idea. We have to make this assumption that a claim is true. Now, we follow a few steps, and we might find statistically significant evidence that refutes that claim. So we already went through this once in the last lecture, but let's go ahead and see how do we do this in general. Well, in general, there are 4 steps to a hypothesis test, as summarized by your Cognitive textbook. The first step is to state your null and alternate hypotheses. That's H naught and H sub 1. You want to think of H naught as a statement of no difference or no change, and this is key. No difference, no change. Every statistical test has a slightly different way of wording your hypothesis statement. You need some way in general to think about it. Okay, so null as in nothing, meaning no difference, no change. That's what we want to say. Now, what is this similar to? It's like saying the claim is true. Your null hypothesis is saying that the claim made by somebody is true, and you want to refute that. So you come up with an alternate hypothesis, H sub 1. H sub 1 is like saying their claim is false, they're wrong, they're lying to you. It is a statement of difference or change. So you think about them as complementary. They are opposites of each other. Okay? Now, step 2. Once we've got our hypothesis statement, we have to calculate the test statistic. Okay? Now that's looking at those differences between what we observe and what we expect to see. In the last lecture and in this one, we call that the chi-square test statistic, but it might be something different depending on the kind of test that you're doing, and we'll address each one of those as they come up. Very closely related to and often in the exact same step if you're using a calculator as finding this test statistic is to find the p-value. That's step 3. What is the p-value? That's something new. This is a probability, and it's the probability that assuming the claim is true. So the probability that assuming your claim is true, your observations, the things you saw, the data you collected, happened by chance alone. The smaller your p-value, the less likely your observations occurred by random chance. Well, why is that important? Well, if you happen to have a really big difference between what we observe and what we expect to see when we say that their claim is true, but we had something really different, that difference is really, really unlikely to happen. But if it actually did happen, if we observed it, then that's going to give us really strong evidence to state that the claim is wrong. Okay? So the smaller your p-value, the less likely your observations occurred by random chance, and more likely because there really is a difference from what is expected. And that's how we make a conclusion, is by looking at that p-value. So how small does a p-value need to be? Well, we compare that p-value to a significance level of alpha, and this is going to be either given to you or it's up to you to make that determination. Alpha, the significance level, is basically how confidently you want to reject the claim. The smaller alpha is, the harder it is to find evidence against that original claim. Now, you might be given a critical value like we saw last time, and that's very, very similar to alpha. They are basically two sides of the same coin. You may be given a critical value, and that's going to put the p-value in terms of the test statistic. So it's kind of like making the p-value moot at that point if you have the critical value. All you need is your test statistic and critical value, or you need p-value and alpha. Either one will work. Now, once you've completed these steps, you can finally make a conclusion that will either reject that original claim, say it was false, or fail to reject it, saying like, I still don't know if I believe you, but I don't have enough evidence to say that you're lying to me. Okay, so how do we make those conclusions? Well, we have two options. First of all, your p-value is less than alpha, and if that's the case, then you are going to reject the null hypothesis. This is the same thing as saying if your chi-squared is greater than your critical value. And we'll see what we mean when we take a look at these and why. We just have to look at a picture first. Okay? Now, the other option is that the p-value ends up being bigger than that significance level alpha. And if that's the case, then we fail to reject the null hypothesis. We don't have very strong evidence to refute the claim, so we have to reject our alternate hypothesis. And this is the same as if we have a small chi-squared relative to our critical value. If chi-squared is less than the critical value, we fail to reject. Okay? Now, let's go ahead and actually take a look at an example that's going to put all of this into one nice, neat picture. So just to keep things a little consistent from what we did from last lecture, we're going to look first at the chi-square test for independence. And we use this test when we want to see if two categorical variables are associated with each other. That's when we use the chi-square test for independence, two categorical variables. Now, often this shows up in a two-way table. It's similar to the ideas about conditional distribution and independence that we worked on in a few other sections. Let's take a look at this example. A study followed a random sample of 8,474 people with normal blood pressure for about 4 years. All the individuals were free of heart disease at the beginning of the study. Each person took the Spielberger Trait Anger Scale Test, which measures how prone a person is to sudden anger. Researchers also recorded whether each individual developed coronary heart disease, or CHD. This includes people who had heart attacks and those who needed medical treatment for heart disease. Here's a two-way table that summarizes the data. So now this becomes really interesting, because now what we can start to ask ourselves is, we have an anecdotal evidence to say like, hey, when people are angry, their blood pressure goes up and it tends to stress them out, and that increases your likelihood of heart disease. Well, how do we know that's true? Is that just based on what people say? Or do we have statistically significant evidence to prove it? Now we can use some math to try and provide evidence to suggest that the claim is either true or false. Okay? So let's go ahead and take a look. First off, if there is no association between anger level and heart disease, how many individuals with high anger and CHD would we expect from this sample? So if there is no association, okay, now that's important because we learned the formula here to find expected values. Expected value is always based off of no association, and the expected value that we would see with these two-way tables was we take the row total times the column total, and then we divide it by the table total. Okay, I just use this as an abbreviation. So when we go through and we look at this, let's go ahead and plug in and find out what is our row total for each one of these. Well, we're looking at the incident of somebody having high anger and chronic heart disease. High anger there are 633 people with high anger and 190 people with chronic heart disease. So our row total is 190. Our column total in question is 633. And then we divide that by our table total, which is 8,474. And this gives us, in this sample of 8,474 people, if there is no association, no link, one is not more or less likely to get heart disease based on their anger level, we can calculate this. If we go ahead and punch this into a calculator, we get 14.192 so on and so forth. If we round that to 3 sig figs, we're going to see that's going to be about 14.2. So that's how many we would expect to see if there's no association. Compare that for a second to what we see here, 27. That's almost 2 times higher than what we would expect to see. So what should that suggest to you? This is a pretty significant difference to me. This looks like if somebody has high levels of anger, they're going to be more likely to develop chronic heart disease. Okay, well, we need a little bit more evidence than this to get through it. Do the data provide convincing evidence at the alpha equals 0.1 significance level of an association between anger level and heart disease for people like those in the study? The critical value is 15.20. So again, for the purposes of this course, you're always going to be given that critical value. Okay, we showed you before how to use a chi-squared table to find it, but we're going to give you the critical value every time. Okay, so here's what we need to first off do. We first need to recognize, all right, well, what's my hypothesis statement? That was step number 1. So my hypothesis statement, the null hypothesis, is a statement of no change, no difference, or in this case, no association. So we would say there is no difference, no association between anger and coronary heart disease, CHD. The alternate hypothesis, however, H sub 1, is going to be saying there is a difference, there is a change. And in this context, there is an association between our two variables. Our two variables in this case are anger and CHD. Okay? So that's step 1, is writing out the hypothesis statements. So we want to try and refute this no association claim, and we're going to do that by finding more evidence like this, showing a high difference between what we observe and what we expect to see. And the way we do that is by doing this chi-squared test. So the chi-squared test, most calculators will call it a chi-squared test for independence or a two-way test. So we want to write down the name of the test. This is one way that even if you're using your calculator, you show your work. And our calculators on campus are describing it as a two-way test. Okay, so what ultimately are we going to try and prove with this? Well, we are going to say that this two-way table, if it's a chi-squared test, is going to fit a chi-squared distribution. You might start to think, hey, that kind of looks like that norm CDF stuff that we did, right? Except it's not normal because it's not symmetrical. This is skewed right. But the idea remains the same. We are going to find the chi-squared test statistic, which is going to be a value on the x-axis. Okay? And what we're going to try and find is what's the probability that we get something that's even more extreme than that chi-squared test statistic. And this is our p-value. And hopefully this starts to make some kind of sense here, because what we are trying to do is show very concretely that the probability of getting an observation like we did or more extreme is really, really unlikely if it's just to happen by chance alone. Okay? If it actually happened, maybe it's because there actually is an association, not because of just random chance. And if this is a very small p-value, then that should tell us that we have strong evidence to refute the claim. So let's go ahead and get to it. We're going to use a calculator to help us out with this. Okay, so I find a chi-squared test calculator online, or you can use some other kind of calculator, but this is a really simple one to do. Okay, you're going to be offered a two-way table with several rows and several columns. You usually don't need much. Okay, you just need enough to cover whatever you have here, and we had 2 rows, coronary heart disease or no coronary heart disease, and I went ahead and I typed them in here. The low anger, moderate anger, and high anger represent our columns. You'll notice I'm not including my total rows. Okay, so now what we need to do is just go down here after we've typed in our group names, and we go ahead and hit next. And now we're going to enter in the values that we had for each one of these. We had 53 with low anger and CHD, 110 with moderate anger and CHD, and only 27 with high. Then we had 3,057 in this cell. The next cell we had 4,621 people with moderate anger and no coronary heart disease, and then we had 606 people that classified themselves as high anger but no coronary heart disease. We go ahead and click next, and it's going to essentially it's going to ask you what's your significance level. And again, this alpha, this significance level that we see here, the lower this alpha is, the harder it is to refute the claim. And whenever we're dealing with stuff like this with medicine, we actually usually want a really, really small alpha. We want it to be hard because we want to be confident that what we are saying when we refute this claim is actually true, or very, very likely to be true. So we'll go ahead and select the alpha equals 0.01, and we calculate the chi-squared test statistic. And here we see that it might be hard to see, so I'll zoom in a little bit, but you can now actually see that in the parentheses here, we are given the expected values, right? We saw that 14.19, we calculated that before, and with the intersection between high and CHD. Not only that, but we are given our chi-squared test statistic in blue just below the table. The chi-squared test statistic is 16.0768. The p-value is 0.000323. The result is significant at alpha equals 0.01, or the p-value being less than 0.01. So it even tells us if our result is significant with this calculator. Not everyone is going to do that, so I'm going to ignore that for right now. I'm going to gloss over it. We're going to just write out the results that we found here. So we had calculated a chi-squared. This had a degrees of freedom equal to 2. This had a sample size of 8,474 and a chi-squared of 16.1 if we're rounding to 3 sig figs, and a p-value that was very, very small of 0.000323. So that means this area is 0.000323. That's an extremely tiny area. That's less than 1% chance, right? What we're saying is that if there really is no association between heart disease and anger level, then we only had a less than 1% chance of getting data like this, where we see that, hey, somebody with high anger seems to be more likely to get heart disease. So it looks like there's an association. Our chi-squared is this value down here, 16.1 or 16.0768, so on and so forth, which gave me 16.1. It's usually a good idea too to write out your expected counts matrix, or the two-way table of expected counts. You can do that. It's usually not required, but just in case, if you want to actually write out all of your expected counts, the results I had here were 69.73. From that calculator page, 106.08, 14.19, and then in the next row we had 3,040.27. In the next row we had 4,624.92, and then we had 618.81. So on and so forth. Okay, so let's stop to take a look at what these results are actually telling us here, because this is actually really illuminating to me and very interesting. When I first see this, I look at this and I see the difference between high anger and moderate anger, and I start to think to myself, high anger should have higher levels of chronic heart disease, I should see more people. But the problem is we have such a huge difference in the number of people that classify themselves with those anger levels. And that's really skewing our perception here, right? If you look at what the expected counts is, the moderate anger is really not that far off from what we actually observe. The expected counts are very close. But when we look at the expected counts for high anger and heart disease versus observed, that's what we see in the shift. That's what's making the difference. That's what's giving us actually a statistically significant result. Because we look at our p-value, 0.000323, which is the same thing as 3.23 times 10 to the negative 4. That's extremely small. This is very, very unlikely. We make our conclusion now to say that our p-value is less than alpha because the p-value 0.323 or 3.23 times 10 to the negative 4 is less than that significance level 0.01. That should tell us we should reject our null hypothesis. Okay. On the flip side, you can also say that your chi-squared statistic is greater than your critical value. Remember that our critical value was 15.20 and our chi-squared was 16.1. So that should again tell us we should be rejecting our null hypothesis. We have a statistically significant result. So there it is. This is step 4. Compare your p-value to alpha, and now we can write out a statement. Since my p-value is less than alpha, I reject the null hypothesis in favor of the alternate. Okay? So what is that telling us? It's telling us that yes, we actually do have statistically significant evidence that there is an association between anger level and heart disease. That's it. Alright, you guys, thanks for watching this example. Go ahead and start working on your practice problems, and I will see you next time.